Welcome. I hope you guys enjoyed the virtual cocktail half an hour. Andrew from Loft Orbital, Molly from NASA, and I started this meetup with the goal of bringing together the software and aerospace industries, and hopefully these events bring us one step closer to that. So during the talk, feel free to write comments and questions in the chat, and the speakers will try to address that in either real time or at the end in a Q&A session. And so now it's my pleasure to introduce Kai Staats and Ezio Moletti to the talk about SIMOC, which is their high-fidelity model and interface that simulates a human habitat on Mars. So Kai is a veteran software engineer working on all kinds of platforms for science research and education. He co-founded the Yellow Dog Linux operating system, has worked on machine learning algorithms that have been used by LIGO to detect supernovae, and is currently the project lead of SIMOC. And Ezio is a software engineer on the team with over 20 years of experience and is a C Python core developer. Python's something that you guys probably use every day, so thank him. And he's also an avid photographer. So without any further ado, Kai, please take it away.
Thank you, appreciate it. Hope this, I think we've heard this 100 times, but I think it's important to say that I hope this finds everyone healthy in such strange times. And I really appreciate your making time this evening to join us in this virtual environment. It'll be fun someday, maybe to give the talk again or an update talk in person when it's a little bit more comfortable for all of us to come together. So thanks again for joining. I want to clarify one thing. I don't call myself a software engineer. I'm more of an architect. I come up with ideas. I am a programmer, but compared to the guys I work with, like Ezio and Yuri and some of my former team members at Yellow Dog Linux, I'm just the guy who has the ideas and helps pay the bills. And it's folks like Ezio who really make it happen. So I'm happy that Ezio was able to join us this evening. Yuri was not available. But Ezio and I are going to share this presentation. So I have a lot of stuff to cover. And I'm going to jump into the slide deck here pretty soon. We're going to go pretty fast, but at least you won't be bored, and hopefully you won't fall asleep. And we're going to go right up to the demo, live demo of SIMOC. And then I'm going to hand it over to Ezio, and he's going to describe some of the software components, and then we'll be open to a question and answer period. And if we have time at the very, very end, there's just a brief couple of slides I'd like to share with you about a really cool project that comes next. So here we go. And hopefully this works, the share screen works. Okay, and we get the infinite regression of the, the shared screen. Okay, can somebody confirm that you can see my screen? Are you seeing black or are you seeing a slide? Andrew, can you confirm? Adam, sorry, can you confirm if you can see my screen or not?
I saw infinity, and then we can see the arrow, but it's black.
Okay, that's the wrong screen, so just a moment. Let's try this again. Apologize, we're going to share the screen and share the other screen. Okay, how's that? Is that better? Adam, okay, excellent, thank you, appreciate it. So the title of the talk is Becoming Interplanetary, and it's an exploration of long-term off-world habitation with SIMOC. And the emphasis is on long-term, as you'll see when we get into the talk. And again, myself and Ezio Moletti he's currently in Italy. It's very late there, so thank you for staying up for us. And as I was thinking about this talk, I was thinking, well, is this a talk about space with computer geeks, or is this a talk about computers with space geeks? And maybe it's a little bit of both. And I'm okay with that. I think we're going to kind of touch base on everything, and hopefully we appeal to all of you out here who might be in both categories, or one or other category. When we think about long-term habitation of off-world environments like the Moon or Mars or Europa or Enceladus or asteroids, we often see beautiful artwork like this. This is done by a friend of mine named Brian Veerstig, who is a phenomenal space architect. And we look at these images and we look at these sealed habitats, and they look like something we could build today. And it's true, we could. But there's a lot of things missing in these artistic renderings about how we actually are going to survive in these environments. The harsh conditions are often not talked about in both science fiction and even in reality. It's been told to me by a gentleman at NASA, Johnson Space Center, that NASA does not know how to provide a fresh salad to an astronaut every week, either on orbit or on a terrestrial environment. And that seems like a harsh statement, but I think there's some truth to that. And that's a lot of what motivated and started this entire project, started SIMOC, was how do we simulate the complexities required to sustain human life for long periods of time in these harsh environments. So we look to science fiction. Star Trek is one of my favorites. And we have airlocks that never need decompression. We have transporters that instantly move objects from point A to point wherever. And we have food that can be ordered on demand. Don't worry about the greenhouse. Don't worry about the edible and inedible biomass and all the things that go with it. And of course, we have potatoes that are raised out of human feces, which doesn't really work all that well. So we have these environments that we've seen on film, we've read about them in books, and we get excited about them, but there's a lot of things that get in the way. So we have to ask the question, how do we actually do this? And it comes down to one basic, well, there's a number of functions, but there's one basic thing we really have to be concerned about, which is environmental control and life support system. That's what keeps the humans alive. And there are two basic categories. There's physico-chemical, and no, that's not a typo. It really is the word physico. I don't know why. It's air, water, and food, temperature and atmospheric pressure, waste products managed by machines. And that's exactly what's on the International Space Station now. So this is a ground-based replica or a copy of what's on the International Space Station. This is what has kept astronauts alive for more than 20 years. And it's a very complicated machine, and it breaks a lot, and it's very expensive to fix when it's broken. We also have bioregenerative life support systems. And that means that we're working with a combination of higher plants and animals and microorganisms. We're really trying to reproduce the environment that we're accustomed to here on Earth in smaller systems with the least complexity possible. And that's the key. What is the minimum complexity required to keep a human being alive using plants and animals? So a brief history of space farming, which is really quite fascinating. All the way back to 1971, the Soviets were doing some really cool studies in their space station, working with flax and leeks and onions and cabbage. They ate the first veggies grown in space 4 years later. But what's interesting is that it took about 10 or 12 years before we took seeds into orbit, grew the seeds into a living plant, that produced seeds that produced another plant that we could eat. One full cycle took over a decade. Now, partially that's because we're in microgravity. Microgravity makes water do really weird things, and plants don't quite know which way is up, literally. So there's a lot of challenges in that will be reduced when we're on the moon or on Mars, but not completely eliminated. And of course, those experiments have continued. This is the full extent of the bioregeneration attempts on the space station. And this was actually called VEGGIE. I don't remember what the acronym stands for. So we believe that the long-term challenge, the long-term solution to off-world habitation is going to be a combination of machines and bioregeneration, a hybrid solution. So a combination of machines and chemicals and plants supporting each other, working together in combination to support the humans. The closest thing we've come to that is Biosphere 2. I just noticed I misspelled biosphere. I need to fix that. So Biosphere 2 is about an hour and a half from where I live. I just live on the other side of those peaks, as you can see in the upper left-hand corner. And this facility was built in the mid-'80s and was functional with 8 humans sealed inside from 1991 through 1994. Or 92 through 94. It's the world's largest, and still today is the world's largest completely sealed experiment in long-term human habitation. And it's 3.5 acres of a fully sealed buildings. The amount of air lost is less than the amount of air being lost on the space station today. That's how advanced this building was and still is today in terms of what they accomplished. It's really a miracle in architecture. If you haven't been there, I highly encourage you to visit. It's a phenomenal existing research center. It's not just a tourist trap. There are a number of existing, or I should say current scientific and research projects, and they're only growing. They're doing some phenomenal work with their ocean, with the rainforest, with the desert biome. The tour is absolutely fantastic. And as I'll tell you a little bit later, I had a chance to live there for a month last year and conduct my own experiment. This is called Lunar Palace. This is the most recent attempt at a fully sealed bioregenerative environment. This was 2017 to 2019, 3 or 4 different runs for as long as 8 months with 4 astronauts inside. This is China's project. And this is really cool. This is kind of the opposite of Biosphere 2. Instead of these huge environments, they compacted everything into a very small space, computer controlled, computer articulated, monitored. This is much closer to what we're probably going to see in first, second, and third generation human habitation on the moon, Mars, even in orbit, right? So this is something we would kind of expect. Now, the challenge behind this, of course, is that when these guys moved in, all the plants were already in place. They were already grown, already mature, already fully functional. And that presents another challenge, which is how do you build something like this and get it operational with robots? Or do humans come in with seeds in their pockets and literally start with bare soil, in which case you're fully reliant on machines until the plants are mature? So this is something that came out of the Lunar Palace. This is their systems flow. They had a number of these diagrams. This is my favorite. And as you can see, it covers a lot, from storage to crew to condensate treatment, to reclaim water, urine treatment, solid waste treatment. But here's the best part right here, the yellow mealworm. So the yellow mealworm is a way of taking inedible biomass, the stuff that we don't eat, the stalks, the leaves, the shells, the seed pods, the stuff that we simply can't digest. And the yellow mealworm is able to take that inedible biomass and convert it to a fully digestible protein, if you don't mind eating worms. So this comes down to sometimes cultural differences. There are some cultures that are more comfortable with these things than others. There are other types of organic materials and I should say plants and animals that also perform some similar functions. Mushrooms are one of them. Mushrooms or fungi are excellent at breaking things down and of course are highly edible. There's also larger animals such as chickens and goats that are also exceptional at converting this inedible biomass and sometimes waste material into something that we can safely digest. So that takes us to SIMOC. And SIMOC is a scalable interactive model of an off-road community. This was originally a pilot project for the Arizona State University Interplanetary Initiative. We had funding from 2017 through 2019. And it was through this project, started originally as a 5-person capstone team, an undergraduate team that built the first model, and Ezio and Yuri have been part of phase 3 and really helped just convert this into, or take this into its current state, rebuilding the entire system from the ground up. So for those of you who are interested in mathematical models or in programming systems, I want to be clear that this is an agent-based model. What does that mean? It means that instead of having discrete formula, in which we're simply using a spreadsheet or even a Python program, and we've predefined the interactions between each ones of the components of the model. Instead, we're defining each model as having inputs and outputs. So if I'm a human agent, I take oxygen in, water in, food in, I give off carbon dioxide, I give off wastewater, and I give off waste solids. And then there's something else in the system that takes those in. So the plants take in carbon dioxide, give off oxygen, take in the wastewater, and again, the mealworms might be the things that take in the waste product, the solid waste. So in that agent-based model, we've defined each one of the agents, and then we set the model in motion, and those agents interact on a simulated hour-to-hour basis, 24 hours a day. So the reason we do that is because we get complex behavior out of relatively simple mathematical functions. So where we might have just linear functions, something plus something, we end up with nonlinear behavior, things that can go a little bit chaotic, which is exactly what we shot for and exactly what we got, as I demonstrate later. So this gives you an idea of some of the agents and some of the what we call currencies of exchange, those things that move between the agents. This is the SIMOC interaction diagram. I built this in 2017, and this is the original diagram we started with, created by a gentleman named Raymond Wheeler at NASA Kennedy. He spent his career focused on really modeling and understanding these human-in-the-loop closed ecosystems. And a lot of the data that we use in SIMOC comes from his research. He's prolific. Just look up Raymond Wheeler if you want to learn more. And so if we zoom in on this model a little bit, well, let me tell you this. So this is these are the categories of agents: inhabitants, ECLIS, agriculture, ISRU, and then these are all the agents that we've defined. And this gives you a little bit better feeling as you zoom in. Now, not all of these are active right now. This is our ultimate goal, is to have all these active. You can see that we've defined such things as a clinic and a rec center and a studio and theater, a sanctuary, a kitchen, surveyors, excavators, transporters, and processors, a wide variety of things that would help us. At least we're trying to simulate a very, very complex environment. We have about a dozen of these currently active in the model, and we're able to expand now that the model is built. So here's an example of the human agent, the human inhabitant agent I was talking about earlier. This gives you the actual amount of exchange of oxygen and water and food, carbon dioxide, urine and waste and heat. And these numbers all come out of a document called the NASA BVAD, which is the baseline values and assumptions document, and then there's an integral component called Human Integration Design Handbook that fed data into that BVAD. So this is also something that's available on Google Scholar or on the SIMOC website. We have all this available. This is just one example of over 30 different agents. We have about a 3,000-line JSON file that defines interactions between each one of them. So this is the part of the talk where I wish we were in person, because I like to walk into a theater with a grocery bag, and I hand out these very items. For the wheat, of course, I hand out a loaf of bread. And I just hand them out at the beginning of the talk, and I don't really explain why. And then once we get to a little bit later in the talk, we start looking at the actual values. Now, I know this text is really small, so lean into your computer a bit. These are all of the plants that we currently have in SIMOC. These are actually in the model, again, from Ray Wheeler at NASA. And you can see that this is a really, really finely tuned understanding of how these plants grow: rice, wheat, cabbage, chard, celery, and we're looking at their growth rate on average of grams per hour. And then when they're finished growing, for the total number of days, which is the growth period, we have the total amount of mass, and then the amount of edible and inedible biomass. And we've been tracking nitrogen, phosphorus, potassium, potable water, atmospheric oxygen, atmospheric CO2. All of this is in the model. So then we zoom in a little bit and we say, well, if you're going to go to the moon or to Mars, what would you bring with you? And this really harkens back to the Biosphere 2. We learned a lot in the Biosphere 2. It was not, as some of you might have heard, a failure by any means. It was an incredible learning experience. So let's look at the oxygen production of cabbage versus a strawberry versus wheat. We'll check that out. The wheat is far, far greater, by a huge factor, above, in fact, almost 10 times more than the cabbage. So if you want something that's going to take in a lot of CO2 and produce a lot of oxygen, you want wheat. However, if you've ever grown cabbage or grown wheat, you know that cabbage you can eat as soon as it's ready, and it grows quite a bit faster than wheat, whereas wheat takes a long time to grow, and then you have to harvest it, and then you have to process it. So in the biosphere, they say it took 7 months to make their first pizza. There's also sweet potatoes, tomatoes, and green onions. Now look at wheat and look at sweet potatoes. Both of them are incredible producers of oxygen and CO2. It turns out that in the Biosphere 2, they ended up planting sweet potatoes everywhere, in the rainforest, in the desert, in the savanna, along the beaches of their ocean, even in their own domiciles. And they ate so many sweet potatoes that their skin turned orange over time. And the reason is because the sweet potato can be eaten right out of the ground. It has calories, it has a sweet flavor to it, and it's immediately processable into a number of different foods. So briefly, I'm going to share with you, this is an experiment that I ran in 2019. I was there living at the Biosphere for a month in the Casitas, which is a nice place they have a place that holds about 120 people on campus. And so I was running an experiment underneath one of their current experiments, and this is where we actually grew our own barley fodder. Now, barley, as you know, is a very simple grain, or it's a grass, and we wanted to grow the barley in order to understand biomass accumulation, CO2, photosynthetic activating radiation, temperature, and humidity. Those are the 5 things that we monitored. Oh, also water intake. The reason we did this is because if we go back to the data from Ray, these are averages. He took the beginning biomass of the weight of the seed and the end biomass, and all these numbers are averaged over the life of the plant. But that's not how plants grow. They don't grow in straight lines. If for any of you have gardened, you know that you go outside every day and you look and look and look and look, and there's still nothing growing. And then suddenly the next day it's 2 inches tall, the next day it's 6 inches tall. That's a sigmoid function. That's a slow, fast, slow function. That's how plants grow in the real world, especially fruiting plants that we eat. Trees, not so much. So what we wanted to do is we wanted to capture that sigmoid function for ourselves and then reapply that sigmoid function in the Python code in order to take Ray's data, still end up at the same place, still end up with the total biomass, but do it over the course of not a linear function, but a sigmoid function. So this is the real data that was acquired in just the biomass. The other data are different plots. And this is, again, our application of a synthetic function to match that relative curve. Okay, SIMOC demonstration. So first I want to invite you to the SIMOC website, simoc.space. It's a rich, deep website, old school website, lots of drop-down menus because there's just way too much to put on a one-page slider. There's a page for first-time users, for advanced users, which you guys would probably want to jump into. There's one video tutorial. We're going to be doing a lot more. For those of you who might be educators, we have a full next generation science standards NGSS aligned curriculum. It's a 65-page document for grades 5 through 14. We have our full research library. Every resource we use to build SIMOC is available for free online. All of those from Google Scholar, of course, but then taken and updated locally. And we also have a blog for just our updates, publications, and lectures and such. And then if we go to National Geographic, we were fortunate enough, by the way, if you go to SIMOC and you go to Launch SIMOC, that takes you to Nat Geo. We've been working with Nat Geo for over a year and a half, and they have been patiently awaiting the launch of SIMOC, which happened just 1 month ago today. So I'm really excited to give this talk today because it's been just 30 days and the server has not crashed, which is the coolest part. So SIMOC, we've partnered with National Geographic because they're all about education. They have a web portal called the National Geographic Education Resource Library. And on that portal, they have 4,000 applications, of which we are proud to say that SIMOC is now one of them. And so we encourage you to go to their website and check it out. Lots of cool stuff. So now we're going to actually look at SIMOC. So here we are at the SIMOC site, and we're going to go ahead and sign in. And I'm going to go ahead and do a new configuration. Now I'm going to choose a preset. We have 4 presets, one human plus radish, 4 humans plus garden, and I'm going to go through just 2 of them here, and then I'm going to hand over to Ezio so you can talk more about the software. And you'll see that in that preset, we have Mars, we have a 10-day duration, very short mission, we have a small crew quarters, we have 1 inhabitant, 100 kilograms of food, which is plenty, 1 life support system, no greenhouse, we have no plant species, we have a small solar array, and we have a battery. And over here on this side, we have a table of contents which takes you through and talks to you about each one of these items over here. So if you want to learn more about the crew quarters, it's right there. If you want to learn more about the greenhouse, it's right there. And then on the graphs, which becomes more relevant when we actually start introducing plants, this tells you about your solar production by your current solar array, and this is how your power is being consumed. So here we go. We launch the simulation. And we're up and running. It's always good when a live demo actually works for a live presentation. So you can see that the simulation was almost instantly generated, and I now have a scrubber at the bottom. So in this simulation, I'm going to go ahead and let it play, and we'll speed it up a little bit. So you'll see that we have, this is the amount of power produced, the amount of power consumed. This is the amount of CO2 produced and the amount of CO2 consumed. And so what we're looking at here, these spikes are when the ECLIS rack, when the mechanical life support system turns on and activates. So we're going to go to consumption breakdown. And right here on the right-hand side is our, this is basically the now point. This is what's happening right now. So you'll see that right now there's a CO2 removal agent activated. Now watch what happens as I step forward in time. As soon as we're past that point, it turns off. Now the CO2 agent is off. And so we'll go through and keep playing. And now it's back on, and now it's back off. And what is that doing? It's knocking the CO2 down below our nominal 0.1% CO2. We don't want to go above that. It's approximately 400 parts per million. On the right-hand side here, we have a lot of variables, which I won't go through all of them now. I'll let you do that later. But we track a lot. We track all the different stages of water. We track the atmospherics. We track the food. And as you can see, as we go through the food, the human is indeed consuming food. Okay, So now I'm going to, I want to share that we can download our simulation data and you can store it locally. This is both for presets and your own unique configuration. So if you come up with a really cool configuration, you can save it and share it with a friend. And SIMOC can be run entirely offline. Once you've loaded the interface, you can load your data sets locally, share them with friends, share them with classmates, and run it that way. So I'm going to go to New Simulation. And this time I'm going to go to one human and radish. Oh, well, okay, I'll come back to that. So now we've launched one human and a radish. Now, at first, it looks about the same, but I'm going to change this panel to greenhouse plant configuration first, and you'll see that we have just a small number of radishes versus the total size of the greenhouse, just 40 square meters of radishes. Now we're going to change that to greenhouse plant growth. And you'll see the radishes are just barely starting to grow, but I want you to pay attention to this panel here, the CO2 production and consumption. So as at first it looks the same, right? We still see the CO2 being drawn down by the CO2 scrubber. However, we see additional power being used here. That's because we have grow lights. The grow lights are activated in a certain part of the day. Now watch these peaks. Watch right here. Over time, those peaks get smaller and smaller until they're activating just momentarily, and then eventually they're gone. So what happened? That means that the CO2 scrubber is no longer needed. And that's kind of cool. So now you'll see the CO2 scrubber is not coming on anymore. We have a urine processor coming on, we have some other things coming on, dehumidifier, but the CO2 scrubber is not. Why? Because the plant is actually doing the CO2 scrubbing for us. So now watch what happens as we get closer and closer to 100% growth. At 100% growth, we're going to harvest the radishes. Here we go, boom. We harvest the radishes, they're pulled out of the garden. Instantly, our CO2 production is dropped. The plants are no longer there to take the CO2 out of the air. And we are now once again reliant on the CO2 scrubber. Pretty cool. I always get excited watching this, even though I've done it 100 times. So now I'm going to go back one more time, and I'm going to go through this pretty quick because we could spend an entire session on just this. I'm going to go to the 4 humans in a garden. And now when you come down, you'll see that we have wheat, cabbage, strawberries, radishes, red beets, and onions. We have many more solar panels from 30 to 400. We have 2 battery systems. And now we have a lot more power production, and this tells us how much of the greenhouse we're actually using. And it shows you we have wheat, we have cabbage, strawberries, radishes, beets, and onions. And I'm not going to launch a simulation because we can, but you guys can do it on your own, experiment on your own, and you'll find something similar. But there's some surprises that I'd like for you to discover when you play with it as to what happens. It doesn't go quite as smooth as the previous ones. So even though this looks like this would be a good assembly, it's not the right balance. And that's the point of SIMOC. The point is for you as citizen scientists, as scientists, for all of us as researchers, is to experiment with this incredibly complex environment to discover what is the balance that works long term. How do we maintain not only the right atmospherics, but how do we also maintain the right balance of water? How do we make certain we don't run out of water? And how do we make certain that we're actually putting edible food back into the system for the humans? So with that, okay, and I'm going to go, oops. And Ezio, your turn.
Yes, so hello everyone. So as Kai mentioned, the SIMOC server is an agent-based model, and it's entirely written in Python. We are using Flask, Redis, and for the communication with the client, we are now using WebSockets. We also support a different way of using SIMOC. So right now it's only available on the National Geographic website, as you saw, and is currently running on GCP. But it's also possible to run it locally on a laptop or on a local server. And we are doing this, we are supporting this through Docker containers. So if you run it locally, you can just run with Docker containers, and you can run it on your laptop. But if you want to host it on a server and have like thousands of users using it, like we are doing on the National Geographic website, you can use GCP or AWS or Azure. And the agents support different functions, and like we can have normal, logarithmic, exponential, sigmoid, and even compound function, and each with unique time scales. So some things happen during like day by day. Other things are related to the whole lifetime of the agent. And we also have a command line interface. So if you just care about the data, the number, to process it later with some other tool, you can run it from the command line. Otherwise, if you want to see the graphs or see the number through a web browser, you can use the web browser interface, which is the one that Kai just showed you. So this was the backend. The front end, for the front end, instead we are using JavaScript, and we are using Vue.js as a framework. We can use like different themes. So right now the focus is on Mars, so it only supports like simulation on Mars, but it can be changed depending on what you're using it for. I also show you that we have 4 presets right now, plus a user-defined preset. So you can create your own preset, and there is an interface where you can quickly save it and load it as you go through different iteration. But you can also download presets as local file, as local files that you can then load again. So you can create like a lot of different presets that you can load. And the dashboard is also customizable. You saw before, like I was switching the panels, like when he was showing you the configuration of the greenhouse, for example, or you have like different graphs. So each of these panels can be changed. So you can decide what to show depending on what you're interested in. And you can also add or remove panels. So it's completely customizable. And you can also save, like once you found a set of panels that works well for you, you can also save that. And finally, the data, the numbers that you actually get from the server. So the server computes all the values, and you get back all this data that you see through the charts and graphs and tables. You can also download this data. And once you download it, you can use them again, even offline, once you have SIMOC running. So instead of asking the server to calculate and send the data, once you calculate it once and save the file, you can load it again, and you can go through using the same interface and the same panels. You can go through it again to observe and see finding patterns in the numbers and in the graphs and in the charts. And as I mentioned, right now the focus is on Mars. So we are simulating a Mars habitat, but the system itself is flexible enough. The way it's designed, it makes it flexible enough that you can use it for a number of different applications. For example, from microbiology to even stock market trades, if you wanted to.
So at this point, Ezio, is there anything else you would like to add? I know my slides on the software side of it was relatively brief. Is there anything else you'd like to add before we move into the questions?
No, I think it's fine. If they have any specific question, we can answer them later.
Okay, excellent. So Adam, if that's good, we wanted to keep it short, so we have lots of time for questions. We can always do additional demonstrations if people are interested, if we have time.
Great. Well, thank you so much. I thought that was absolutely fascinating. And let's give them all a big round of emoji reacts, I guess.
Virtual applause.
Yeah. And so then in terms of questions, so it looks like we got a couple that I wrote down. And so as I'm asking these, please write more questions that you have. Again, a lot was covered, and so there's a lot to look into. So the first one is the software free? And I would add to that, is it open source? And if any one of us wants to contribute, how could we?
Good questions, thank you. So coming from a Linux background, having spent 10 years running TerraSoft and developing Yellow Dog Linux, for those of you who might remember the good old days of Linux on PowerPC, Of course, we have a very strong foundation and belief in open source. We have not open sourced this yet, and part of the reason is that we're still in development. There's always a good time to open source once you have your foundation in place. So that is our ultimate goal. We haven't set a time for that yet, but it will be, once we open source it, of course, it will be free. And we haven't determined exactly what license we put that under. In terms of contributions, yes, we would love to have some seasoned engineers and some newbies on board. We are a relatively small team of just 3 right now. And myself, I mostly listen in and ask them, can you do this and can you do that? And then they laugh at me and say, why can't you do it? So the more people we have with fingers on the keyboard and assisting in either JavaScript or Python or even server-side management would be fantastic. So we would welcome that input.
And how could they contact you if they're...
Yeah, so the best way is if you go to the SIMOC webpage, there's a contact form and that goes directly to me. That's probably the best way.
Great. So another question that came in, I'll ask this in terms of, you mentioned looking into obtaining the right balance of parameters to ensure long-term survivability. And it looks like Anthony was wondering, have you ever looked at applying reinforcement learning to this environment?
Yeah, that's a great idea. Within our team, we have quite a bit of background in artificial intelligence and machine learning, and so we have talked about that. And it'd be a lot of fun to do reinforcement learning and to have some kind of machine learning algorithm actually learn from the behavior of SIMOC and then eventually take control of SIMOC and automate some of that convergence onto the perfect balance of all these different variables. That is something we'd like to do, and that's probably going to be starting next year. We still have quite a bit of fidelity that we want to bring into this model before we feel that it's good as it is, but there's a lot more we want to do before we feel that it's ready or even worthwhile to bring the machine learning algorithms in. But absolutely, and if that's something that somebody wants to take on, they could start now. We could give you access. I should be clear, we also will give access to our GitHub repository for those people who are on the team, so absolutely. If there's somebody who wants to take on that project and start playing with it, that'd be fantastic.
Great. Looks like Henning asked about, is there documentation that describes how to set up the agents? And I saw you actually did have very extensive documentation, so maybe you could talk a little bit about how that was made, what goes into it, and maybe what's your process for keeping that live.
Sure. Let me kill my slide deck here, and let me show you a couple of things. This document, can everyone see my screen again? Can you just confirm?
Yep.
Okay, good. So this is our SIMOC PRD, our product requirements document. This has been developed for 3 years, and this is the Phase B version as of 1 month ago today. And this is available on the website for free. We have another version internal that's about the same thing, just a few more notes and such. So this document is very extensive. This has a description of every single agent, all the processes. It has footnotes for every piece of every resource that we have, all the research, diagrams. Here's the human agent. This is all of the data that the human agent is built upon. And here's the oxygen thresholds, the CO2 thresholds. This is the definition of all the ECLSS agents. Each ECLSS agent has been validated by Paragon Space Development Corporation, which just 2 months ago landed the contract with NASA to do the life support system for the Artemis mission. So we work very closely with them. A couple of their aerospace engineers are on our team and help us develop this. And so you can see this just goes on and on and on. Here's all the plants. Here's a description of plants, the structures, et cetera, et cetera. So that's the background data. And then this is the agent description file. And this is a single JSON file that stores all of the agents. So we can go down here. Let's find, let's do cabbage. Okay, so here's cabbage. And so cabbage just tells you how much CO2. Let me zoom in here just a moment. Forget how to zoom in on this thing. Oh, let's try this. Oh, okay, this doesn't have a zoom function, forget that. Nope. Okay, so in this, you can see that there is a value for CO2. We have for CO2 input and the growth of the lifetime, the daily type of function. It's a normal function, meaning a bell curve. We have deprivation values, which defines how long a plant can go without something before it is before it dies. and we have potable water, we have nitrogen, phosphorus, etc. You get the point. So those two files together, this is all of the data that is then described in this single file. This file is loaded at the point of launching the server and becomes the foundation for all the interactions. Sorry, that was a little long-winded, I apologize, but I hope that answers the question.
Yeah, I think kind of you mentioned Paragon. Maybe another question is, are there any partnerships that you have, for example, with NASA or other research institutions that would try and use this simulation to design the first human missions to Mars? And then if not, what would be required to productize it for real missions?
Okay, that's a really good segue. Thank you. You brought me into what would be the last slide. So first I want to show the partners that we do have. This project started at Arizona State University, is currently working in tight collaboration with the Biosphere 2 and the College of Agricultural and Life Sciences at University of Arizona. Controlled Environmental Agricultural Center called SIAC is an advanced research center in plant physiology. They've been doing closed ecosystem studies for many, many years, for 20 or 30 years. We work with the Arizona Science Center for the interactive components, Paragon, and although I have to be careful, NASA has not given us funding, so I can't call them a partner, but we do have individuals at NASA Johnson Space Center and Kennedy who have contributed an incredible amount to the success of this, and of course National Geographic, as I described. So let me go back to answer your prior question, and just a moment. So this is, I'll answer now to answer your question. We are now moving into, in addition to SIMOC, we've been working for over a year on the development of the world's highest fidelity Mars analog and research station. This is not a simulation, this is the real thing. This will be a prototype of what we're actually going to build on Mars. Not necessarily architecturally, but in terms of function. So this is a 3D model that we printed of our design, and I took it to the biosphere and photographed it in the front yard. And we have inch-and-a-high astronauts. And so this greenhouse, of course, is not architecturally what we would see on Mars, but this is an existing structure that was used in the 1980s while they were building the real biosphere. There were 3 women who consecutively lived in this for up to a month at a time, completely sealed from the outside world, living entirely from the plants that were growing inside, both for their atmospheric recycling and for the water and for the waste products and food. So this SIMOC and SAM, this is called SAM, and these two together are a system. So SIMOC gives us a mathematical and computational engine to simulate these complex behaviors. We're going to keep working on the high fidelity, or the fidelity of SIMOC, giving it more interactions, more agents, closer approximations, fine-tuning those mathematical relationships to get as close as possible. But ultimately, we have to tie SIMOC into the real thing, into something that's real. So we're going to remove the simulation function of SIMOC and tie it directly into live data output from sensors, from hundreds of sensors inside of this actual habitat that we're going to station at the Biosphere 2. So now SIMOC will be learning from the data that's being generated by this research station. And then we rebuild the database and all of the JSON files and the functionality of SIMOC based upon the real data, and that's where the artificial intelligence comes in. Once we get those two interlocked, SIMOC becomes a learning tool and a control tool in which we can then do positive feedback into the environment through the reinforcement learning and take control of SAM from the simulation engine itself. That's our long-term goal. We're currently in the fundraising for SAM and for this analog.
That is really cool to hear that it could eventually be used for direct control. We have some more questions coming in. One is, have you ever considered modeling emergencies such as rapid depressurization or radiation events that could damage the environmental control and life support system? Yeah,
I'll start with that, and then I'll hand it off to Ezio if he has some more ideas and feedback. And I apologize. As you can see, it's getting dark here, so I'm disappearing in the view. So in the original version of SIMOC 3 years ago when we started working on it, it was more of a game design back then. And that was actually one of the first things we wanted to do was simulate entropy. We actually have built into the underlying structure of SIMOC, although not active now, what we call an entropy engine, which is a knob that you can turn that increases or decreases the stochastic behavior of the model. So that's actually there in the underlying code. We haven't integrated it or activated it yet. The long-term goal will be once we get the fidelity to its nominal level. And again, SIMOC is a research tool first and foremost, and then an educational tool. And eventually we'd like to add some of those stochastic behaviors so that we have things like micrometeorites smashing a greenhouse and everything dying in one greenhouse, or a airlock seal breaking, or a compressor motor dying. Once we're able to integrate those things, then we've got something really, really interesting. But we've got to make certain, before we start making it game-like, we've got to make certain that the underlying research tool is functional and has been demonstrated in the real world. And Ezio, is anything you'd like to add to that from a programming standpoint, or?
No, I think you answered the question.
Okay.
Another one is, so if I wanted to adjust the simulation to some of our own systems, those are the files we'd have to modify.
Ezio, good one for you.
Yeah, so all the behavior of the agents is defined by the JSON file that Kai showed before, even though it wasn't really clear. But basically, we have this JSON file that describes each individual agent with all the inputs, all the outputs, all the function. So just by editing that JSON file, you can add a new agent or change the behavior or define your own agents. So if you have a system and you find which are the agents in your system and how they are connected with each other, then you can edit this JSON file to basically create the agent that model your system, and then you can use SIMOC to run it. Does that answer your question?
Looks like it.
Yes.
All right. Another question from Molly is, has SIMOC been, maybe you could speak to how it's been used for educational purposes, and maybe what you see as the vision for that.
Sure. Because we just launched 1 month ago, we haven't, and schools just letting out, we haven't had an opportunity for SIMOC to be incorporated into a large number of classrooms. However, in October of last year, and then again in May of this year, April and May timeframe, National Geographic has a board or a panel of professional educators. It's called their Education Review panel, and they actually preview and use all of the software before it goes live on the National Geographic website. And these people are certified with Nat Geo. So we had 2 different experiences where we gave SIMOC to those teachers and said, hey, go run with it. And in October, it was a lot of things breaking, server going down, typical things that happen to new software. However, in the last round, we got some really positive feedback. And if you go to the SIMOC website, there's both an example of a curriculum that one of the teachers built for her 8th grade class, or was it, I think, 6th grade class, where she took our next generation science standard curriculum and integrated into her own interactive curriculum for her classroom. And then she did video interviews with the kids. It's fun. It's super, super fun to see what they came up with. So that's our first experience. We have 2 or 3 other teachers who have done something similar. And we're looking forward to getting a lot more feedback, especially next fall when the classes kick in again, to see how SIMOC is used in the classroom.
Great. Looks like another question is, what is the largest simulation, maybe in numbers of humans, that you've seen? And maybe you could also speak to what are some of the limits to scaling your simulation further for larger groups.
Ezio, you probably know the numbers better than I do. Do you want to, on what the limitations are right now on the interface? I'm throwing it at you.
Sorry, I was on mute. Okay. So I was saying that the limitations are mostly related to the processing power and the time. So you saw the simulation, the presets we run, they load in a few seconds. More complex simulation can take minutes. And that's pretty much how far you can go on the Nat Geo website. So the system we have live on the Nat Geo website has this limitation, mostly because we don't want people to run simulation that takes hours, since it also has a cost. When you run it locally, you can remove this limitation. And we also support something that we call a single agent, which basically allow us to treat like a number of agents of the same type as if it was a single one. So, for example, if we want to put 100 humans, we can make it look like it's a single human that eats and breathes like 100 humans. And this speeds up the computation significantly. So there's basically no difference between having 1 or 100 when we are using this single agent mode. But the complexity comes up when you don't use the single agent, or also when you have like a lot of different agents. For example, in the greenhouse, we support several dozen of type of plants. So you can plant all of these different plants, and since they are different agents, they need to be each individual value has to be calculated differently depending on which plant it is. Whereas if you just plant one single type, even if you have like a high number of plants, as long as it's the same kind, you can use the single agent, so it doesn't really matter. So the simulation that we ran so far, we had like some even running for years, because that's another factor that of course affects the computational cost. So how many steps you have. So SIMOC, I don't think I mentioned, but it works by the hour. So we calculate all the individual steps hour by hour. And of course, if you run a simulation that is 1 year long or 2 years long, you're going to have like thousands of steps. And for each step, you will have numbers for all the occurrences and all the agents. So what we did, we ran simulation like for 1-2 years. We usually have like 10-20 humans, and the greenhouse, you can see on the, if you try it, you have like the full garden that has like, I don't remember, like 10 different type of plants. So this is what we have.
Great. Well, if anyone doesn't have any other questions, one maybe last question. I know you kind of left us with a teaser of homework to check out SIMOC and look at that kind of unexpected finding. I'm wondering if you could talk about any other unexpected or surprising findings that maybe went counter to your intuition, but you learned about through this simulation.
Yeah, that's really, thank you. That's a good question. I think I'll start with having developed software, been on software development teams over the years. I find that even though we designed the software and we know what's happening inside, to see emergent behavior in something that we developed, but we don't always understand what the emergent behavior is, and we have to go diving in deep to investigate within our own model, that tells me that we succeeded. And we find ourselves doing that a lot. I often build spreadsheet models to match the functionality of what's happening SIMOC point to point to make certain that it's working properly. And so one of the things that came out of it that really taught me a lesson is that we think often about things as being unidirectional. We think, well, I need oxygen from the plants, but we forget that the plants need carbon dioxide from us. And I know it sounds relatively simple, but I remember the first time that I couldn't understand why the plants were dying. Well, it turned out the plants were dying because there weren't enough humans. But we don't think of it that way. We think of it as, well, we need enough plants to support the humans. We also need enough humans to support the plants. And I know it sounds simple, but that kind of interactive and interreliance behavior is what makes it so fascinating to run this model. And that's where you start to get this chaotic behavior where you'll see plants not growing. You'll see them stalling or stagnating or not reaching their full potential biomass within their given growth period because they're simply not getting enough light because you didn't put enough solar panels, or they're not getting enough carbon dioxide because you don't have enough humans, or you have too many plants for the given space. And that's the kind of interrelationship that gets really complex and really fun to see how it works. Hey, by the way, Adam, I see a time is up. Does this automatically terminate our call in 2 minutes and 48 seconds, or is it just a warning?
Yeah, I guess it looks like we have a hard stop at 8 p.m.
Okay, well, there you go. I just want, you can see on my screen here, I just wanted to show this. We were talking about the agent, the JSON file that describes the agents. We do have a web interface for building those agents, so you don't have to do it all by hand. I just wanted to share that.
Cool.
Yeah, it needs a little work. If anybody wants to take on a project, we could use somebody to take this to the next level.
Right. Well, I think this has been absolutely fascinating, and as evidenced by 100% clap emoji, I think everyone else thought so as well. So thank you again so much for sharing with this with us, and I hope that members of our community will get in touch with you about perhaps how they could contribute.
Yeah, thank you very much. I forgot to mention, we do have a Facebook page. You can search for Mars Hab, and or just contact me and I can point you to it. We'd love to hear from all of you again, and thank you so much for taking time to attend.
Cool. All right, thanks. Bye, everyone.
Thank you. Bye.